last time?
We will not hear him because I'm muted.
Please unmute.
No, it's here also.
Hello, can you hear us? Thumbs up if you can hear us, because we cannot hear you. Okay, great. Okay, Shana Tova to everybody. Maybe we can clap some hands for the new year. We are counting year 5,783. That's the Jewish count, and it's a great pleasure to have you, many friends with us over here. And also, a lot of people actually were broadcasting this to people in Florida and in Washington. So a lot of people on the Zoom. So thank you very much for joining us, everybody, for this very special event. For me, it's just absolutely a great pleasure to have Dr. Alex Tendler visiting us from Israel. And we are going to basically honor the new Jewish year with having a little bit of honey and apple for all of us to have a very, very sweet year with a lot of success and achievements. And we have some custom that we also bring some kind of data share and knowledge and using it also to promote good deeds that actually can save humanity. And if everybody question why we call you here today, we call you here today because we have a message of hope. And the message of hope that we will relay here would mean that with God's help, with the blood and sweat of Alex and the team in Israel, we believe that we can provide a solution for a lot of people that have very serious cancer illnesses already in 2024. So I would allow Alex to tell you a lot more about that. Just want to start and say, guys, can you, thank you. I just want to take 1 second and just tell you what is my involvement with ExoProTher. So actually, I know Alex Tendler for more than 20 years. We were both working at Intel in Haifa together. And at a certain point, he decided to join his father and go to do PhD in the Technion in brain science and to join the very important research that his father do for 20 years. And open ExoProTher. And we met in Pier 22 in San Francisco by accident, and he told me about the great magic that he's doing, and I was just telling him, okay, why you are not stopping everything that you do and just going and give all of yourself to that? Say, yes, I would gladly do that, but I need a little bit of something to begin with. And I'm very proud to say that I was the first investor in this company 5 years ago. And just looking back at the journey that we did during the last 5 years and where we are today, and I will allow Alex to share with you the amazing things that happened in the last 5 years. It's just a great pleasure and a great mission that we are on. So with that, I will just send it over to my dear friend Alex Tendler to tell you a little bit about ExoProTher Medical, and we will take a Q&A also from the people on the Zoom. There is a chat going on, and if you want to ask questions, we will dedicate a few minutes for Q&A afterwards. So please, Dr. Alex Tendler.
Okay, thank you, Shai, for a kind introduction. Your glasses. Okay. Okay, so ExoProTher Medical, we are inspired by evolution, developing breakthrough oncology therapy. This is my partner, Dr. Lana Voloch. We my co-founder and CEO of the company. She is responsible for the business part and the regulatory part. And I'm a CTO and responsible for technology and science. We working together 5 years in ExoProTher already, and met even before, a couple of years before, in at the startup that we work for. Well, I will start with P53 protein. P53 protein is the guardian of the genome. So it protects our DNA from forces outside. For example, if you have too much UV on your skin, your DNA can be damaged, it's actually damaged. And P53 stops the cell cycle and trying to repair the damage. If it's successful, it lets the cell to continue. If it's not successful, it just kills the cell. It's a kind of programmable cell death. It's called apoptosis. So it is a very important part of what we are going to talk about. So our therapeutic content based on delivery of P53 protein, the guardian of the genome, using exosomes, which are extracellular vesicles, to the tumors. Now, I told you about the function of P53, but it's important to say that it's mutated in about 60% of cancers in humans. And those cancers are the most aggressive cancers and therapy-resistant cancers. Regarding the exosomes, it's something actually very new that was discovered as a possible treatment or about 5 years ago. Before that, they were considered like a waste of the cells. Today we already know that it's kind of intercommunication between cells to maintain homeostasis of the body and connectivity between different tissues. So they are very low immunogenic, and they can pass biologic barriers. For example, like a brain-blood barrier. If you some drug, most of the drugs, if you inject them into the blood, they actually don't reach the brain. It's not like this for exosomes. They can pass this barrier and enter the brain. So what we do in one sentence, we deliver P53 using small nanoparticles called exosomes. Now, all this actually based on discovery, as Shai said, my father discovery. He found that in corneal epithelial cells in eye, actually there is no cancer, or it's very rare. And he go to look what's happening there, and it turned out that it's a very big amount of P53 in those cells. While in regular situation, other cells in the body, it's very tiny amounts of this protein, and it's always inhibited. But here it's a big amount of this protein, and it's already stored inside the vesicles. Here we see electronic microscope picture of P53 inside the vesicles, and it was taken from tears of the animal. So we have it in the eye, in the tears. And it's correct for every vertebra. It's correct for humans, it's correct for reptiles, amphibia, and birds. So we take advantage of this mechanism, and we want to do something different. So when due to UV, when some cell in cornea can be damaged by UV, and there can be a mutation of P53 protein, so there is no protection anymore from the cancer. But instantly, this cell will get a healthy P53 by these vesicles from the neighbors. So it's kind of local mechanism of defense, anti-cancer defense inside the cornea. Now, cornea, it's immunoprivileged tissue. There is no blood supply there. So immune system can't fight the cancer like in other parts of the body, for example. So it's only local defense against the cancer. So we take advantage of this mechanism that develops for 100 million years. Actually, all, as I said, in all vertebrates, since the unicellular organism start to be multicellular organisms. So we found the tissue with abundance of P53 and transfer to surrounding cells by exosomes. Now we kind of do the same thing, but systemically. So we started with harvesting those cells from chicken cornea, from just slaughterhouse from the beginning to make a proof of concept. But today we're already growing those cells in incubators in laboratory. We're working on immortalization of those cells so we can do scaling, and very close day that we will able to grow a very big amount of those cells inside bioreactors. So we're translating ancient local mechanism of anti-cancer defense into the novel systemic therapy. So we can just inject those exosomes into the bloodstream. Now, P53 was discovered more than 40 years ago, and there was a lot of attempts to try to create cancer by delivery of P53 to tumors. Unfortunately, it was unsuccessful. One of the reasons why it was not successful is because P53 works as tetramer. So you need 4 molecules of P53 to function. When it's mutated in some cells, you have big amount of mutated P53 inside. If you provide a new functional P53 to those cells, it's just inhibited by the mutant P53 because it's statistically impossible. It's always will be much more mutant protein inside these cells. It's called the dominant negative effect. So we found the way to overcome it, and we use actually chicken P53 instead of human. Now, chicken P53, it's similar enough to perform the work, the job of the human one. But it's different enough not to aggregate with the mutated protein. So it can work by itself as soon as we provide it to the cell. Okay, so I'll jump straight forward to the results. It's old results. It's 1 year ago we achieved very nice in Vivo study. This is colon cancer that was injected to immunocompetent mice, meaning with immune system, intact immune system, and the treatment was performed using chicken origin P53. So it's like chicken to human, chicken to mice. It's not same species. And as you can see, we achieved full tumor growth arrest following 2 injections of the treatment. Here on the lower panel, you can see actual tumors that was taken from the mouse after the experiment, and you can see that the smallest tumor in the control group is the biggest tumor in the treatment group. So here is the treatment group. Some of them did not have tumors at all. We also did some histological studies and see increased apoptosis and reduced angiogenesis. Okay, another study that we performed was survival study. It's also same colon cancer, mice colon cancer in immunocompetent mice, and what we saw that we can achieve prolonged survival of those mice. Each knee like this, it's mice that died due to cancer. So the exo group lived more, and some of the mice actually continued to live and died from natural reasons. They were cured. We also didn't see any signs of toxicity or immunogenicity, and we also saw reduced metastasis. So in control group, you can see in abdominal area a lot of nodes, metastatic nodes, while in created it was very few of them. Now, last December we got investment by Israeli biotech fund, $1.5 million. And except the money itself, it's very, very important to mention that Professor David Sedzansky, who is actually a co-founder and managing partner of IBF, is a distinguished oncologist and researcher in the area of P53 specifically for more than 20 years in Johns Hopkins University. So it's make a difference for us. Because till now, nobody could believe that chicken P53 actually will work in human cells. So after this investment, we got some milestone that we supposed to achieve, and it's here. So we were supposed to screen different types of cancer and to show that we have actually broad application, different types of cancer responding to our treatment, and we need to provide direct confirmation that there is a P53 mechanism of action actually in this treatment, and to perform in vivo study using human cells, human cancer. So one by one, this is a little bit complicated, but I explain everything here. This is two examples of GBM. GBM is a brain cancer. This one is a human cancer, this one is murine cancer. And what we can see that after single application, more than 80% of cells actually in apoptosis. Apoptosis is a programmable cell death. So the cells still there, but they are dying. And they are the way to show what is the condition of the cell. So less than 20% of cells are alive, and rest of them are at apoptotic state. And the same we have also in murine GBM. And here we can see cell cycle arrest, another thing that P53 is responsible for. So it can kill the cell, it can also stop its division. So cell cycle arrest is the situation when cell is no more dividing. Also very good achievement. Okay, then we go to the colon cancer panel. It's 6 different types of colon cancer, human colon cancer, with different status of P53 mutation in it. In this one, it's wild type P53, so no mutation for P53 at all. What we see here, it's dynamics of cell growth, control versus treatment. So how we did it? We took a petri dish, we put the cells and put it under the microscope for 4 days, and then we picture every hour. After 4 days, we perform kind of a movie of this, and we can see the confluence of the cell on the petri dish. So how much area actually the cells cover. And what we can see that in control group, it's going to full confluency, while in treatment group, in all cases, we see the reduction in growth. Then we go and perform same tests of apoptosis, and we see that also in most of the cases, after single treatment, we have very extensive rate of apoptosis. For here, it's very high. Here it's almost not reacted, 1 of 6, and here again, very good response. This one we took for in vivo studies, and this is the same as for colon cancer, but ovarian cancer. Again, 2 of 3, very high, very strong responses to the treatment. It's every time it's only single application of the treatment. Now, this is a little bit complicated, but very, very important slide. So you need to concentrate. What's happening here is it's like this. When P53 is functional, it translates other proteins that do job for it. For example, protein P21. P21 stops cell division. It's example. And it's a responsive gene of P53. So if we see that P51 is elevated, means P53 did its job. Okay? So we applied P53, we applied our vesicles with P53. It's chicken origin vesicles. And then we measured the response using PCR, like for COVID-19. And we measured the mRNA, mRNA of P21, and we see clear upregulation. So this is actually the first time that we will able to prove, first of all, that the mechanism of action is based on P53, not something else. And also, I think we are first in the world that show that animal origin P53 can actually function in human cells. And it is big deal. Now, last but not least, it's actually a study in progress. I got this update yesterday night. This is an in vivo study that we initiated 2 weeks ago or something. We have 3 groups of mice. This time we injected human colon cancer to these mice, so it's immunocompromised mice. They can stand the injection of xenogenic cells, human cells. And we have 3 groups. One group is control, it's not going to be treated at all. One group is early treatment. We start treat on day 5. And another group, it's late treatment. We didn't start treat at all, so I don't know what's going to happen here. But after first injection of the early treatment on established tumor, it's important to say, it's small but established tumor. We already see the difference, and this difference is statistically significant. And I'm waiting for the next measurement. It's supposed to be in, I think, in 5 hours or so. So it's going to be very nice. Well, now about the indication that we are targeting. So, as I said, it's about 60% of cancers that have P53 mutations. But in some cases, it's even higher. For example, GBM, glioblastoma, brain cancer, it's above 90%. Ovarian cancer, above 90%. Lung, bladder, colon, between 60 and 70% mutation. So those indications are very relevant for us. And it can be, of course, combined with regular therapies like chemotherapy and radiotherapy. And we believe that it will be enhance their function. This is how our program looks like. Actually, in the beginning of 2022, we start all stuff that I presented, and we successfully finished it by now. And now we are looking for Series A investment, about $10 million. And we plan to be first in human study somewhere in the beginning or middle of 2024. Important to mention, we have 2 patent family, IP families. One is oncology treatment, as I presented. Another one is antiviral treatment. It's because P53 also involved in antiviral protection. And I mean, it could be a papilloma virus, herpes virus, and stuff like this. To summarize, we are a preclinical stage company. We fully own our intellectual properties. It's fully ExoProThers. We have completely innovative approach, different for everything you can see. We target oncology indications of high unmet needs. It's exceptional breadth of application, and very important, we have experienced and passionate team. We're already 8 people, 8 scientists, 2 laboratories in Israel. And as I said, we are looking for money.
Okay, thank you very much, Alex. It's a great pleasure to have you. I know that it's a little bit comprehensive, but whoever wants to get another shot at the slides or to talk more. 2 questions that I want to refer to you. First of all, if you can return to the important slide that you have there.
This one?
Yes, this one. So you mentioned basically that we are harvesting the P53 with the exosome, your particle, from chicken.
Right.
And you basically created a response in a human protein. Why is that a breakthrough, and how is that helping us with the scientific community?
Yeah.
What was the problem there, and why is that so important breakthrough for the company?
Well, it was hard to convince scientific community for 5 years, I would say, that something like this could happen at all. And in the beginning of trying to find the funding, the most problematic thing is the chicken protein. And but it's also the solution. But now, when we already proved that it's working, it's changed the game.
Another question that I just wanted to present, if you can just go to the slide when you show the different percentages of cancer. Maybe just to clarify a little more. So my interpretation of that, at least, is that if you're looking at brain cancer, 9 out of 10 persons with brain cancer is actually a potential to receive our drug. Is that the right way to look at it?
Yeah, we hope so, yes.
Okay, so basically the percentage over here represents for each type of cancer, right? What will be the sort of likelihood to be selected for a clinical treatment using our drug? Is that right definition?
Yes, yes. But now we are mostly targeting colon cancer. We are also thinking about GBM, but it's a very hard application. And from one side, from another side, if you give another 2-3 months to this patient, it's make difference. So we will see.
Okay. Any more questions from the forum? Okay.
Thank you.
Thank you very much. Thank you very much. Okay. Now we can drink.
now we can have beers and wine.
Just a minute. Yeah.